Hi everyone. Hi Lachlan. See you're here and already ready. Good. Awesome. Let's wait the canonical 5 minutes to start. In the meantime, if you want to add your name to the meeting minutes, we'll share the link in the chat.
Hello. Sorry, I just discovered that I have had no audio output. Uh, if you were giving any
Yeah,
instructions, I apologize. I didn't hear them. I
you
guess
you
just
we can hear you very loud and clear now. So
wonderful. Thank you.
yeah, people are joining. Oh, hi Jimmy. You're also here. Great.
Oh, yes.
We had a preview of this work from Jimmy at one of the Verizon weeklies back in November, I think it was, right?
Yeah, it was in November, Thomas.
Yeah.
Yes.
So we're happy to see an update here.
At that time, it wasn't open source, but glad to see that it is now open source.
Yeah, thanks to Aalto University for re-implementing parts of this so that they could be published as open source.
Cool.
Okay, that's good because I feel bad kind of standing up and um, presenting this like this is my baby and not Jimmy's.
It was joint work from the beginning also with all the other people listed here.
We might be a bit low in numbers today because holidays. I think in Europe, this, the Easter long weekend, people tend to take some days off on the back of that.
We are
Yeah,
recording this, right, Thomas?
Yeah, yeah, it's all recorded, of course. But yeah, 1 minute to go. Okay. Right, so we can start. Today, we welcome Lachlan from the Computer Science Department at Aalto, who will be presenting a paper, the paper Trust Me, Self-Verifying Remote Attestation Evidence, a project that he, Jimmy, Zainab, and other at Aalto and Ericsson Research have been working on. What can I say? Yeah, but it takes this project takes a fascinating approach to verification, which basically radically simplifies the verifier's works, and it makes Verizon useless, basically. But I won't spoil any more, and we'll now hand over to Lachlan with just one question before we start. And I leave you the controls. How would you like to take questions? Is it at the end or in line?
No, I think we can do it. We can do it in line.
Okay.
So I
Okay.
will, yeah. So maybe one thing I'm going to say is I think part of this is to show some new work that is hopefully interesting. But we do have a couple of kind of concrete and perhaps to you there may be a bit boring and tedious questions about the practicalities of how we're actually kind of building this thing. So if I don't want to kind of suggest that everyone's going to be so interested that we're going to have trouble getting through to the end, but just in case that happens, I will probably try to move things on and skip some slides to that point in the last few minutes. But
Okay.
yeah, please, I appreciate any kind of questions or comments or anything as we go.
Can you see the participant list? So can you see the
Yes.
Okay. So you can control the admission to the queue. I don't need to do any arbitration here. Okay, cool. Take it and go.
Great. Thank you very much. So yeah, I'm Lachlan Gunn from Aalto University in Finland. So I want to talk about some work that has been done with Ericsson, as well as collaborators in the Elastic project from Ghent and others who have given lots of useful input that aren't mentioned here in the list. So what the problem that we want to solve here is that okay, you have this idea of you have your attester, you have your verifier. The attester knows something about itself, but it wants to convince the verifier of that. It has its protocol, where I'm saying protocol in the broadest, technical sense, where this could be something like a digital signature. But you have some protocol where you're sending this information to the verifier, and at the end of it, the verifier is convinced of the state of the attester or whatever properties it is that are meant to be transferred. And the problem is that different kinds of attesters are going to have different kinds of attestation protocols, which is a problem because now this verifier needs to be kept up to date and it needs to know about all of these, and you have this kind of massive, potentially n-squared problem of keeping everything compatible. So frameworks like Verizon, like Trusty, like lots of others, well, like I guess these are the main ones, can ease this a lot by separating out the verifier from the relying party. So now you have this one piece of software like Verizon that implements all of these attestation protocols that can deal with all of the different platforms, work out all the verification logic, and then send it off to the relying party. So the problem, though, is that you still have this issue that now you have this verifier that needs to be kept up to date. And, in some sense, it's easier because now there are fewer of these entities floating around. But it's also maybe a bit more complicated now because the verifier is going to be some security critical thing that might affect lots of people and is going to be, operated by, really paranoid professionals who probably don't want to, incorporate a lot of software updates if they're not critical to security, and probably don't want to add support for a bunch of plugins from vendors that they have never heard of or really care about. So what we want to do then is to try to get around this problem by having the attester providing their verification code to the verifier. So now the verifier doesn't need to know about all of the different platforms that it's going to talk to. The attester just has to be able to tell the verifier how does it validate the attestation evidence, send that across to the verifier, and then the verifier deals with the problem. Sorry, did someone say something? No, okay. So this, you could say, well, maybe this solves the problem, but it introduces a bunch of new problems because what if the attester sends malicious code to the verifier? Now you're in the same problem that you had before because, well, everything is now compromised and you can't trust anything anymore. But this is the same security problem that we have on the web. And we have lots of implementations of web browsers and runtimes for JavaScript and WebAssembly and all kinds of things that are designed to download code from untrusted places online, run them without any verification or user intervention on devices that are full of sensitive personal data. And we kind of accept this, and it usually doesn't lead to disaster. So these sandboxing techniques exist, and they're already quite robust. So this solves that first problem. How can we keep the attester from compromising the verifier by sending bad code? But there's still the problem of how do we actually trust this verification logic? Because this is just something that the attester has provided, and if we don't trust the attester already, how do we trust the verification code? Well, the solution is simple. You just measure that verification code, and now it's just another claim that needs to be checked. You have a reference value for the verification logic, and this can be validated in a non-platform specific way. And you have the platform specific verification code, which is provided by the attester, and so both of these problems get solved. Does anyone have any questions kind of so far as to the basic principle here? Okay, good question. So yes, it's WebAssembly. So what would the verifier code look like? So at the moment we are using WebAssembly. In principle, you could use other things. Things like eBPF, for example, have some nice properties. But we've used WebAssembly because it's quite easy to port existing verification code to this. Because, there's all these tool chains that can already take existing Rust and C code or whatever, and they can take this Rust and C code, compile it to this WebAssembly, and off we go. I saw a hand up, I think.
I had a hand raised earlier, but the conversation moved on, so I decided to lower it. Should I ask now? Can you go back to the previous slide?
Yeah.
In terms of trusting the verification logic, are you imagining that the verification logic is supplied per evidence? Meaning, if I have, let's say, two different builds of software or firmware, I'm going to have two different instances of verification logic.
So the thinking was that you would have this verification logic that is, let's say, per TEE platform. So you would take what the code that would be used to validate, let's say, TDX evidence. Intel can produce this, or someone else can produce this, and then that gets distributed as part of the kind of platform software that is used by the attester, and then the attester can pass that on. I say Intel could produce this. It doesn't have to be actually done by the TEE vendor, but let's say you could imagine if this became a super popular thing, then that might be one way that would happen.
So is the attester passing it as a binary blob, or a attester passing a pointer to the verification logic to the verifier?
We'll come to this in a minute. So
okay.
Yogesh.
Yeah, so I just one question, like I think similar to what Dhaval has asked, if there are n attesters, are we kind of multiplying similar data on the wire coming from n attesters? Are we duplicating the logics?
No, so we don't have to do that. You could do that if you really wanted to, but it's not necessary because we can use kind of existing infrastructure for caching this. Yes.
Thank you.
Thomas.
So I think it's a follow-up on Yogesh questions, because I'm concerned with the case of composite attesters, where you have a a single device that hosts separate root of trust that independently produce evidence, but that evidence needs to be bound together in a single cohesive thing. So how would binding work in that case across all the different sub-evidences and the associated verification code that each of them needs to? Okay,
So I have a slide for this coming up. So
okay, sorry.
as well. No, it's good. I appreciate the questions. Okay, so we're using WebAssembly for this. I guess many of you are familiar with WebAssembly already since you've asked about it. For those that don't, it's an application virtual machine that, let's say, does similar things to what the JVM would do, but it has a memory model that lets you compile just normal C and Rust and whatever software into WebAssembly modules that have their own isolated memory spaces and defined imports and exports, and are very cheap to spin up on demand. So you can do this quite granularly. And there's also now this idea of a component model, which provides a really well-defined API and kind of a language for describing this API that lets you compose these things into larger components. And so later on, when I talk about composite attestation, this will, I think, be a useful kind of tool. But and I don't want to kind of go into the details of this. This is the interface that we've defined for our verification code, but this is also something that's maybe under development, so I don't want to get too hung up on the exact details of how this works. But maybe we can now show this kind of architecture. So we started off with vanilla trustee. So you have your evidence coming in as an attestation request, and this will be parsed, and then checks will be made, and that's going to produce a claims map, and then that's going to be checked against a policy and some reference values. And then you get an attestation result that gets signed, and you end up with a signed EAR format output. So you have your platform-specific evidence coming in, and you have your platform-agnostic result coming out, plus some platform-specific reference values. But the thing that we noted is that the platform-specific code is all in this part here, where you're parsing the attestation evidence and then checking the endorsements. So what we did is we took this and put this into a WebAssembly component behind a component model interface and say, okay, well, we can provide this via the attester. And so now all of this logic has been taken out of trustee, and we have a platform driver that, rather than doing anything platform specific, just knows about WebAssembly. And it can call into this component that's been provided by the attester, whether directly or through a link. And then it can validate the evidence and then put those claims into the output. So WebAssembly also has some kind of interfaces that you can use to access stuff outside, and this is also really helpful for porting existing software to this. So we can have like an isolated file system region that gets used for caching, so that if you have some code that is going to get some collateral or do some pre-computation or whatever, you don't have to modify that. That can just be put into this WebAssembly component. You have to maybe adjust it a bit to use the WebAssembly interfaces, but it can still take its data, save it in a file, and then read it back on demand. We also provide network access, or at least we have the ability to do that, so that you can have components that access OCSP or fetch collateral and so on. This has its own issues because you don't really want that network access to be abused. But let's say if you have a component that's signed by some trusted provider, let's say it's signed by the TE manufacturer, then maybe you can make this work. But we also want to get rid of this, and I have a slide later talking about some of the ways to do that. But as I said before, we implement this as a platform driver in trustee, and we have a wrapper format that's using EAT and CMW to provide this platform-specific evidence. And then the idea is that we can specify a component ID that's going to verify the component. If you want to send that component over the wire, then you can put that in CMW, the CMW wrapper as an endorsement. But you can also just specify this, and I think it's not implemented yet, but we're going to make this so that you can get this using an OCI, Open Container Initiative, repository from something like Docker Hub, for example. So you can just send a hash of the verifier or some other identifier that would be used to download it on demand and then to cache it each time. So I see there is another question. So can I provide a brief sample or list of things as examples that a sandbox WASM can validate about the host it's running on? The safety and security of sandbox virtual machines also tends to isolate a process from being able to figure out the reality of where it is running. So yes, and in some sense, okay. I think this is kind of an advantage in this case, that you don't really want the component to know a lot about where it's running, because that then causes problems for compatibility. So you don't want this verification component to be tied to a particular verifier implementation or to a particular anything. You would like to be able to take the same verification component and ideally run that trusty on x86, trusty on ARM, or Verizon on any of the platforms that it supports. So yeah, the more you can kind of hide, the better. Having some things open makes having some things open is helpful from a porting perspective, because if you have something like a verification library that expects to be able to download collateral from the TE vendor's server, then it's obviously easier if the component can just directly access the network. But this may not always be desirable. Okay, so then questions about what prevents the verification component from lying. Nothing prevents it from lying, but the key thing is that what we will do is we will insert a claim in the output about the identity of the verification component. So now, when you check this, when you check the output, there will be a reference value for that verification component. And at the moment, that's just the hash of the component. But in principle, this could be something about the identifier, like it could be signed by someone, and there could be some kind of PKI based claim, but we don't have a strong opinion on that at this point. Yeah, and then sorry, there's one from chat, and then I'll come to you, Deval. So who signed? Sorry.
If the code if the verification logic is being signed, then you can imagine that there could be updates to the verification logic. There could be replay attacks, replace the newly signed code with the older signed code. How would these situations be addressed? Because the relying party can't necessarily be expected to know about every possible version and release. They're just trying to trust the verifier to get the latest and not deal with any of these problems.
Yeah. So in our prototype, I should say that in our prototype, we haven't done this, but there are a few ways that you could deal with this. So the first, but most of these are the same things that you would have with existing kinds of PKI. So you could have expiration dates on the on a signature that's associated with the verification component. So if you want to say that, okay, this verification component is going to be signed by the TE vendor, or at least whoever has developed the component, then they include an expiration date. And then the attester, if they want to continue using this, then they would need to go back to the TE vendor every now and then and request a new certificate for their component that they're going to send to the verifier. So that would be one way. The other way would be just to go all out and use ICSP. But
so we are talking about very short expiry up here. Because
Potentially.
when you write piece of code, you don't necessarily know how long it's going to be valid for.
Right, but the certificate can be updated as needed because it's the attester that has to deal with this stuff, and so the TEE vendor already has their code running on the machine, and they're already having some service that's going to download collateral and do registration and so on when the machine is initiated. So as part of that process, they can provide the whatever collateral is needed to validate the freshness of the implementation, or at least of the statement that the implementation is up to date. So the code might last forever and ever, but you might just certify it only for a short time at a time. At least that would be one solution.
Sorry, I may not have followed. I almost felt that you implied the T vendor is involved when the T is created. That is not necessarily always true. So I do think that since nobody can predict how long their code is going to last, then we are going to end up with fairly short expiries up here in order to force the caches to be purged and latest code be downloaded.
Right, yes. If you want to do it without having online checks by the verifier, then yes, you would have to do something like this.
Okay.
But you could also have an online check by the verifier, for example.
You're talking about OCSP.
Yeah, basically OCSP.
Okay.
But yeah, I think this is at least what we were, or at least what I was imagining to solve the problem. I mean, does this seem like a reasonable solution to you, or does it sound a bit too inconvenient?
I want to discuss the current approach for verified development. It's also possible that the two approaches can be combined. I think one of the reasons for the current fragmentation problem, which is where you started the presentation, is that the verification logic is unique to components because the standards didn't exist. So imagine that I, as say a T vendor, am compliant to concise evidence and I use concise rim and I don't do any spec extensions. It's all standard EAT on evidence side, all standard quorum with no extension on the reference value side. Then the verifier logic that's already written in the quorum spec, that should just work.
Yeah.
Now, the reality is that there is a missing step or some missing pieces between the time the quorum spec produces the ACS and the year is generated. And I can talk about it a little bit, but ACS is not year as we already know. So there is a little bit of additional step required. But if we were able to, let's say, define certain standards for transformation of ACS to year, then would we need to worry about this problem?
No, I mean, if everything is already standardized and then you don't need, then there's only one implementation that needs to be in the verifier, then you don't need to do this kind of thing. But the other idea here is that this will allow us to have these different verification kind of mechanisms, even when this standardization doesn't exist. If everyone was using compatible formats for this, then yeah, life would be easy and maybe this problem wouldn't be a problem.
Understood.
But yeah, my enthusiasm with this is kind of growing out of frustration of doing a bunch of academic kind of projects with DEs and having to kind of mess around with verification libraries. Like every time I start some new project, and it's always been a little bit of a pain. And so the idea of, well, we have kind of one library that's going to deal with everything, and that doesn't need to be set up individually per platform, that was attractive to me. But this is kind of a grumble that I have as an academic doing lots of short-term projects. If you're in the situation where you can get everything to be standardized in the first case, then yeah, this is less of a problem.
I completely agree with you. Thank you.
Great, thanks. You
Yeah, just I will be quick. So, as part of the appraisal is a very important aspect of appraisal policy, application of appraisal policy for evidence in a verifier, which presumably in your flow that is still left with the core verifier, where this logic is preceded and then you apply that policy. So, are you saying that your logic will be given to a standalone verifier, which can then make the whole complete verification flow?
So
Is
at the moment at the moment the way that we do this is we implement this into Trusty as a platform driver. It produces a claims map that's then going to be validated against a policy by the already kind of standard code. So this is the current approach now. We could put more stuff into the component, and actually this is one of the slides I have at the end for like this is what I kind of said as maybe a pressing question. Can we put more and more stuff into this component and check reference values? Because when you do layered attestation, and this is a really useful feature to have. I would like to put more and more stuff into here, but there's also part of me that is aware. Okay, people have done so much work on RATs and kind of other parts of this architecture. So saying let's stuff everything into the verifier. Maybe that's not. Maybe it may be kind of doing a maximalist solution to this from the beginning is maybe not so appreciated by everyone.
Sure. There might be deployment problems, or there might be other problems you might hit when you try to build everything in one single version.
Yeah.
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 Okay.
But
I don't know.
definitely
Yeah.
something that would be a possibility. Yep.
Yeah.
Any other questions, or should I continue?
Please go ahead.
Okay, so at the moment we have two implementations of this. One of them is public. There's a GitHub link here. So we have this as a standalone library. So this was just published in the last day or two. So this is very freshly up. And we have open source implementations of verification components for both SNP and TDX. There are some that we're not able to make public. That are for another one for SNP and another one for TDX on Azure, with a non-public prototype of the trustee modifications. And we've been able to take our open source components and then run these in this other implementation. So this, hopefully provides some, I guess, some evidence that, based on the interface that we've developed, someone is able to independently implement the same thing kind of again and have it work sort of off the shelf with an existing, with another implementation. And so this kind of thing, at the moment, they're both trustee, but, in principle, there could be a Verizon one as well. And then you could have the same verification logic used in both platforms, and then it wouldn't be necessary to develop the same drivers twice. Yes, Osama.
Yeah, hello. Basically, there is a problem in trustee. So we have formally analyzed that. And the thing there is that it has no connection downstairs to the actual TLS connection. So it could be possible that basically what you are getting from the evidence is actually not coming from the genuine server that you wanted to have, and rather being coming from completely different server, which is basically someone which is an attacker in the middle and acting as a genuine server. So that's a problem that we have already discussed a few times in the SIG already, and I was wondering what was your motivation for using trustee as the basis for this?
We're using trustee because it is a kind of well developed. It is like a quite mature implementation in Rust that has support for lots of different platforms that we're able to take and incorporate into these components. We're not claiming to solve all problems with trustee, and we're not trying to rewrite all of trustee's interfaces and so on like this. We are kind of focusing on the narrower issue here of how do you validate the claims made by the hardware specific evidence. How those are bound to a TLS connection or to something else, this isn't something that we're trying to address here.
Right, but I mean, when you say mature, that what does that actual mature implementation means? If it's insecure, then the whole process is broken, right? So I don't really understand what you mean by implementation of Rust is mature for Trusty.
Basically, it's not. It's let's say it's something that is supported by like developers who are actively developing it. That's not us, and that other projects do use and do deploy, and so this could be potentially incorporated upstream one day into these.
Yeah, but I mean, still, I don't really understand. Like, if other projects are using it, it's not a guarantee that it's secure, right? So my main concern is about security and not about what who is using it, or for example, like what processes you are using it. So my comment basically is more general to that. What I'm saying is that even if all of the things that you develop are secure, the protocol that you are using is insecure. So the whole really the argument of getting from the hardware or whatever you are getting from whatever things are there in these claims, if they are not properly transported over to the other party, then the whole security argument breaks, because it's the man in the middle or the relay attacker that you are talking to, and not really the actual server that you wanted to talk to. So if all the like the evidence was, all the claims were correctly let's say measured, and all these were collected correctly, even then you have a problem, because you're not transporting, or you're not even talking to the right server that you wanted to talk to. Rather, you are talking to the man in the middle. So that's really my concern about this work.
Sure, but Usama, this is a problem at another layer, right? The one that Lachlan and et al. Are attacking. So it doesn't matter to them, because as
Yeah,
soon as the lower layer protocol is fixed or whatever, then they can
It's
still,
not, Thomas, it's not,
there's
it's not,
nothing to change in their proposal. Yeah.
I mean, it's
yeah. I mean,
not
you
on
can use
the,
this with post handshake verification if you want. There's nothing stopping you from like incorporating this into TLS however you like. This is completely agnostic um, to that. Ultimately, the point of this is that you can get a quote from TDX, and you'll get a claim that has the report data. How you bind that report data to the TLS session is it's a separate issue from what we're trying to solve here. And I think in this we don't want to try to link this to things like TLS and so on, because there are lots of applications for attestation other than TLS, and we don't want to kind of tie ourselves to any one of these. I mean, personally, the things that I use attestation for, they tend to be, they tend not to be things like attested TLS. I usually use attestation in projects that I've done in a non-interactive way, because I want to incorporate this into some like protocol, like in the same way as a signature. But
I'm-
anyway, I mean, my point is that I think this is at a different layer. If you fix kind of whatever protocol issue that you have with Trustee or Verizon or whichever other system that you're using, then the changes won't affect this, because this is something that is just a platform driver. It's not anything about how the evidence is bound to another protocol instance.
So let me try to clarify more about. So I see two arguments. Let me try to segregate them separately. So Thomas is saying that it's a different layer. I completely disagree with that. So basically, it's not necessary to do the TLS at the like the attestation at the TLS layer. You can do it at the application layer. So it's not necessarily correct that we are talking about different layers. So I don't really understand Thomas' argument saying that it's a different layer. It's
The
not.
argument is that this is not a remote attestation protocol that they are describing. That's it.
Right, but I'm
It's
saying
just
that
an
if
evidence format. That's it.
so if the evidence format does not include that binding, then what else will include that binding?
The
But it
binding
does
is
include the binding, because it has the TTX report data field as part of one of the claims.
So if you don't have that binding, then the format, there is something wrong in the format, right?
The
So the
format has
design,
the format has the binding, allows you the binding, because say TDX has its own report, whatever, ARM as their claim, and whatever. That's not the problem. The evidence format is not a protocol, and what they are describing is an evidence format. So whatever protocol transports that evidence format and binds the evidence format to the underlying secure channel is a different kind of argument, right? And topic.
but what I'm saying is that they are using trustee, right? So they are transporting it. It's not only the format, they are actually transporting it using trustee.
But
Is this?
they could use envelopes and put that things in on paper. It doesn't matter.
I don't
Yeah,
understand why it doesn't matter. Like, I mean, the slide is saying platform driver implementation, so it
Because
has
it's a
to do.
platform driver.
So,
That's why it doesn't matter. It's not a protocol.
so what is trustee? Trustee to you is not a protocol, is
No,
it?
Ah,
it's a verifier implementation.
so it's a piece of software that you send your evidence in, and you get an attestation result
Trustee
out that has
starts at
claims for
request
verification.
parsing. Usama, trustee starts at request parsing, that box there. It doesn't care about the incoming arrow, how that thing is realized.
So it would not have anything on the. So if I remember correctly, so there was something like I dealt it with it a little time ago, but so my understanding was that it has something like R car. So something you send a request, you get some back
Right,
some.
so there's another box in the trustee architecture, which is the relying part, the key broker server, which is not in this
Right.
picture, is in front of this picture. So the protocol you're talking about, which is the key broker service protocol, is outside of this slide. It doesn't care about what is in this slide, and vice versa.
So it's basically assuming that all the keys are essentially already provisioned. The system is ready to go and it's only just transmitting it over a pre-established connection. Is this correct?
Mhm.
Okay, thank you.
John.
Yeah, thank you, sir. I think some of us are having a little bit of confusion is the fact that the executable code is the thing that provides the answer and asks the question and is it makes me feel a little uncomfortable. I've done a lot of WASM related work in live PDP and a number of Web3 protocols, but it seems like listening to the previous conversation, there's a disconnect between something akin to a remote procedure call and the implementation, the signed implementation that is qualified to answer that. And I think there's some concern of running executable code from a remote server, even if it's signed or not, and that it would make us it would appease some of our things if there was an RPC framework, say JSON or something like that, whose request could only be answered by a signed authorized component, be it in WASM or whatever. It just seems like there's too much coupling between the implementation of the thing that can answer the request and the arbitrary request itself, which should be human readable JSON kind of stuff. Does that make sense?
Yeah, so I mean, I can maybe just clarify a bit as to how the platform driver does this. It doesn't kind of just take this bundle of evidence as input and then let this produce whatever EAT token it wants. But the idea, and we will get to this, I think, in the last slide, is that it is producing an EAT token that includes a claim that comes from the platform driver, so outside of the component. So it includes extra claims that specify which is the component that produced this result. So it's like at the moment, for example, you would, and sorry, I'm going off script, so please correct me if I'm getting technical details wrong. But at the moment, you would see that, okay, this has like a TDX EAT profile. So I'm talking about TDX a lot because I happen to have a TDX machine under my desk and have done a lot of work with that. But substitute any any implementation. So, the idea would be that you provide this input, and then it's going to produce as output EAT in some format that says this is, so before you would, you would get this TDX profile EAT thing from the verification service, and then you would use the normal like Jose or JWT stuff to validate that using the signature that's attached to that. And the idea here is that rather than validating the public key with a fixed signature algorithm, in a sense, you're saying that okay, the public key is actually this identifier of the code, and then if that is okay, then
Can I ask a follow-up question then? If we follow the workflows of standard containerized compute and microservices, where let's pick Docker, and I need to spin up something from a trusted Docker repo as a developer, as a company, as a some kind of entity that's out of band, I can host my own trusted Docker repository in that context, and it seems like I would want to be able to have my own trusted signed respondents in the context of a trust me implementation that I could point to something local or something on-prem. I may not want to give out to a third party, trusted or not, the means and mechanisms with which to verify something that would validate my own internal corporate security or my own and in the age of claw code or OpenClaw and whatnot, the ability to have these trust frameworks is going within a subnet or an enterprise environment is going to become much more important. And I may or may not want to share that attestation proof with the rest of the world in some kind of public trusted repository. I may want to host myself. Does this framework facilitate that?
Yeah, I mean that's almost exactly the goal of this. That rather than having to use some external attestation service that's going to take this platform specific thing and then turn it into EAT or whatever to be verified, the idea is that because this is in this component, you can then execute the component internally. You can try to say that okay, we will only take components from some trusted internal repository if you want to restrict that, or restrict it to certain components of certain signers or whatever. But kind of compared to the other one, the previous kind of methods, this is much more kind of compatible with doing things fully on-prem, because all of the platform specific stuff, it doesn't need to be hosted by some service hosted by the TE manufacturer. You can do that in place, and then the TE manufacturer will just distribute that code as needed so that you can host it yourself without the deployment problems that would happen if you were just using native code. Does this answer your question?
Yep. Thank you. Very excellent answer, and thank you very much.
Great, thanks. So yeah, kind of just moving on from here. So we have implementation. We have some tests. So there is a few milliseconds of overhead. We are putting this into a sandbox, so you'd expect there to be a bit of overhead, though it comes pretty close to native. So if we do kind of the basic one and we do all of the crypto inside the sandbox with the as WebAssembly code, we are getting a fairly substantial overhead, and I don't want to downplay that, but there's kind of upcoming and ongoing standardization work for cryptographic acceleration with WebAssembly, so that WebAssembly code can access accelerated cryptography from outside. And so to try to work out what is the performance going to be like once this kind of standardization has been realized, we basically added an interface to allow the component to access some like certificate validation stuff, so that this can be done with high performance outside, and then we can see that the overhead becomes much more reasonable. Yes, Osama.
Yeah, I want to check out my understanding is correct. So what I'm hearing is basically you have when you say an accelerator, basically it's GPU, for example, which is doing the cryptography and sending back quickly the results. Is it kind of correct? So what do you mean
No,
by
I mean no. I mean more things like for example, when in ARM you have kind of these various kind of crypto accelerator things. So I wouldn't say it's called, is it CryptoCell? Is I think the ARM one on Intel ones, for symmetric, there's AES-NI, and then there are some other ones for doing elliptic curve things. So more the CPU extensions that let you do this stuff pretty quick. With WebAssembly code, it has to be done in maybe a little bit more generic way, and it's not always going to be possible for the runtime to work out that this bytecode corresponds to a cryptographic operation that the CPU knows how to accelerate.
so I'm trying to digest it. So the way I understand is basically there is something between the CPU and the accelerator. The accelerator basically does that encryption, and you are saying that's on chip for, let's talk about Intel TDX. So you are saying there is an on chip accelerator which is kind of doing this acceleration. Is the data between so how is that communication between the two, and is it encrypted, or how does that happen? So is there a attack like te.fail, ytap.fail, and bad RAM and all that? So how do you kind of protect those?
I mean, it's just a CPU instruction. So whatever, however that's microcoded, that's however it happens to be. So it's like it's the same as if you were doing it in native code, basically. So it lets you shell out to a native implementation of this cryptographic functionality, rather than depending on Wasm time or whatever other runtime you're using to translate that to an efficient implementation of your algorithm.
Like, I mean, these attacks exist also with the CPU instructions like edeport and all that. So te.fail, I mean, exists also with all these instructions, isn't it?
Usama, one clarifying question. Do you understand that this code executes on the verifier side, not on the attester side, right?
Oh,
This acceleration is on the verifier and not on the
and
attester end.
oh, thanks for that. So actually, I was thinking about the happening
Yeah, I
on the.
suspected that. That's why
Okay,
I
sorry for
interject.
that. Okay, thanks. And one more question, Thomas maybe can help here more. So is it not mutual attestation? It's only the attester which is being attested?
You're just validating the quote. So it's like you have
No,
something
no.
like the
I mean,
QVL one, you have some like quote verifier thing that's going to take a
no,
quote
no.
as input,
It's
spit
it's
out an
it's
output,
Yeah.
yes
it's
or
going
no,
it's
the
going
report
it's
body.
going it's going very far from what I'm asking. I'm asking is it mutual attestation,
No,
or
no, no,
is
no.
it
It's only attester to
it's only
verifier.
one way? Okay,
Yeah,
okay,
one way.
thanks.
Okay, so this is trust me as it is now. So I'll kind of just try to. Oh, sorry, there's a hand up. Do I?
Uh, I have a question related to executing all of this code in a security enclave, such as, say, using a confidential compute mechanism. Have you run into any issues or have you prototyped that? Just trying to understand what is the level of support in available in there to execute the WebAssembly or other capabilities you might have required to make the whole thing work.
Do you mean like running the verification component in like inside a like a DE environment?
Yes. Yes.
We haven't tried to do that. I mean, if you've got something like TDX or whatever, anywhere that you can have this kind of JIT code, then there aren't any then there isn't any problem with that. Um, but yeah, we haven't done any like experiments with this. We've just been running this as native code, because it's the logic being it's on the verifier side. So unless you're trying to then attest the result of this to the relying party, then it's probably not um, um, then it's not like a obviously necessary thing, I guess, maybe from our perspective. At least it's something that you could do if you wanted in a particular application, but at the basic level, it's not required.
Sure. I was just trying to let me clarify the context. The question was inspired by your comment on the current inability to do crypto or use the host crypto accelerator capabilities. So it wasn't a question
Okay.
about theory. It was, I know technically it's all at some point in time it's going to be possible. I was just trying to understand the current state of art. Meaning, if you're
Gotcha.
trying to
Yep,
do
I
it, what
understand.
problem I will run into?
Yep. No, so the problem is that the verification code is described with the black bytecode instruction set that is kind of divorced from what the actual CPU is able to do. So we don't have access to the platform specific um, kind of crypto instructions inside the runtime or inside the component.
Okay.
Thanks, Thomas.
Yeah. So I was curious about the lead attest the attester architecture, and in particular, who pulls the various pieces and puts them together and signs them. So how did you realize the sort of compositional aspects, right, where you pull evidence from the platform and the workload, and then you bind it with the evidence verification bit into something that then is shipped to the verifier. Who does that job? How the things are interrelated? What kind of binding are in place? That kind of high level
Yeah.
overview, if possible. Thank you.
Yeah, so we haven't really done so much on the attester side. I mean, from like what we've done is we've basically said, okay, we've come up with a format that says, okay, you just have to stuff your evidence into a JSON thing with this template, and then send that off in place of your normal evidence. But in principle, you just get your platform specific thing and you wrap it in some JSON and send it off. That's the functionality that's needed from the attester side, plus whatever is needed to just keep this component up to date.
So just a follow-up question. Did you have to modify the tester component not in Trust, in Coco to do that? Or are you doing something completely custom?
So we haven't tried to modify any of these yet. This is something that we are kind of working on at the moment. What we've been trying to do is do some work with Kata containers so that we can attest kind of containers from in there. But this is ongoing work that we don't have.
Right. Okay. So it's work in progress. Thank you.
Yeah,
Thank
this
you
is
for the
work in
question.
progress.
Cool.
Yogesh.
Yeah, just a follow-up question is, without the verification logic, what would be the size of the evidence in your exercise versus when you stash the evidence verification logic? What is the delta of the size of the payload, evidence payload?
I don't have the number of bytes off the top of my head, but it's the size. It's this stuff minus the size of what
Yeah,
else.
roughly what percent increase, or maybe a rough ballpark percent increase?
Maybe a few percent, I guess.
Okay.
Pastor, do you know off the top of your head? Can you? I've seen some like SNP ones that are kind of kilobytes, in which case it's going to be like, I guess, 1% or something.
I don't know exactly any size difference on top of my head, but we just add the size of the hash, I guess.
Oh, okay. You're only adding the hash. I thought that you are sending some logic, right, to the verifier.
Right. You could also send it alongside if you wanted, and then that's going to be a bit big. But you can also just send the hash, and then the verifier can download that from some repository and then keep that cached for future requests. So it
Okay.
would just be a one-off addition.
Okay. And you pass the location of the URI in the evidence, or?
Yeah, this is still a work in progress for this one. At the moment, we are using the CMW wrapper and sending it alongside, but the plan is that we're going to provide a URL or a hash that's going to be
Okay. So
downloaded
my
using
origin.
OCI.
Sorry, we need to
Yeah.
close
Okay.
the call down. So
Sorry.
unfortunately, it's a great presentation. Thanks very much,
Thank
Lachlan
you so
and
much.
team. And if there are any follow-up questions, like Yogesh, sorry for interrupting you. Please
No.
post them to the Slack channel or on the list. And I think
Yeah.
Lachlan is there, and Jimmy
Yeah.
as well. So yeah. And Lachlan, if could you please upload the slides to the meeting repo, or even
Yes.
forward them to me so that I can do the work for you.
Yep. I already posted them in Slack before the call. So
Awesome. Thanks very much. And see you next week.
Great.
No, in a couple of weeks.
Oh,
Sorry.
a couple of weeks. Yeah.
Cheers. Bye-bye. Thank you.
Thank you.
Thanks. Bye.
Thank you. Bye.
Donc, par contre, c'est dans une situation